Okay, in this example I'm going to work through this example problem, which you will also find on Moodle, where we have the function f of x equals 2x cubed plus 3x squared minus 180x plus 10. And there's these 6 steps, A through F, which I will work through here, and you will have a similar example for your homework. All right, so part A just says to find the derivative, which I'll do here quickly. The derivative of f using the power rule is 6x squared plus 6x minus 180. And then it says to factor it. We can factor out a 6 here, and we get 6 times the quantity x squared plus x minus 30. And we will continue to factor. That factors as x plus 6 times x minus 5. Okay, we'll come back to that later. Part B says to find the second derivative, f double prime, and so this up here was f prime of x. And so f double prime of x, we'll use the power rule again on that, and we get 12x plus 6. Alright, part C says to find the x values where f prime is equal to 0. So that's above, right here. We'll use this in part C, and f prime of x equals 0 when either of those factors are 0. So when x, of course 6 is never 0, but when x plus 6 equals 0, that gives x equals negative 6. And when x minus 5 equals 0, that gives x equals 5. Okay, so these are these two places where the first derivative is 0, and we'll see later that those are points of where we either have a relative min or a relative max. Continuing on in part C, we're supposed to find the intervals where the derivative is either positive or negative. So you can see here I've split up the x-axis, the number line, from negative infinity all the way up to infinity. And we've made our cut points at negative 6 and 5 because those are the values where the derivative is 0. And I'm going to pick an arbitrary point in each interval to use as what we call a checkpoint. I'll just write this here, checkpoint. And here we could pick something. I'll just pick, let's say, x equals negative 10. Here in this interval, I'll pick x equals 0. And up here, I'll pick x equals, say, positive 10. You can pick any number in those three intervals, pick a number in each one. And then we're going to evaluate the derivative at that checkpoint. So here I'll take the derivative at negative 10. That's going to give me some value. I'll work that out later. Then we'll evaluate the derivative at 0. And here we'll evaluate the derivative at 10. And the reason we want to do this is on that entire interval, the sign, either positive or negative, will tell us whether the derivative is positive or negative on that interval, which will tell us whether the function is increasing or decreasing. When the function is increasing, we will have a derivative that is negative, below 0. And when the function is increasing, we'll have a derivative that is positive, above 0. So I'm going to calculate these values by plugging each of these checkpoints into our derivative. Our derivative, remember, was up here, 6 times x plus 5 times x minus 5. Okay, I did a few more steps here. I plugged negative 10 into our formula for the derivative and got positive 360. When I plugged in 0, I got negative 180. And when I plugged in 10, I got positive 360. So we have a positive, a negative, and a positive, which means our function, f, the original function, is increasing on this interval, decreasing on the interval from negative 6 to 5, and increasing from 5 to infinity, which I summarized in this statement right here. In part D, we determine where the second derivative is 0. This is going to lead to our possible inflection points. I guess one inflection point in this example. So the second derivative is 12x plus 6. We set that equal to 0, and that's going to be 0 when 12x equals negative 6, or x is negative 0.5. So again, I take my interval, and I made negative 0.5 my cut point, so that gives me an interval on the left of negative infinity to negative 0.5. and on the right from negative 0.5 to positive infinity. I'm going to plug in some checkpoints here when x is negative 1 or when x is 2, and we're going to evaluate the derivative at those points, second derivative. So f double prime of negative 1, we plug negative 1 up in here, and we get negative 12 plus 6, which is negative 6. That's negative. And when we plug in x equals 2, we get f double prime of 2, which is 12 times 2 plus 6. That's a big number. That's 30. That's positive. Okay. So the second derivative is negative. This means that f of x is concave down. We talked about that in class. And the second derivative is negative. And here f of x is concave up. And concave down means it has this shape. And concave up means it has this shape. Okay, back to part E now. Part E says classify the x values as locations of local mins or local maxes. Give the corresponding x values. So our two x values were negative 6 and 5. And we saw that f changed from increasing to decreasing when x was negative 6. In other words, it was going up, and then it was coming down. So this means we have a local maximum. Oh, the cat's jumping on me. At x equals negative 6. And we saw that we were decreasing and then going to increasing. I'm at x equals 5, so this means to local minimum at x equals 5. And I did some calculations. I went back to the original f function that we started with. I plugged in negative 6 and 5, and I got those values. So that's going to be the y value of our function at those 2 points. So we will say here we have a local maximum by local meaning it's the highest in that area, of 766 when x equals negative 6, and we'll have a local min value of negative 565. It's much smaller when x equals 5. And part F says to classify, if we go back up here and look, identify the points of inflection. Well, we found that the second derivative, we went from concave down to concave up at that when x was negative 0.5. So this means we have an inflection point when x equals negative 0.5. I'll go plug that in and give the value here. Okay, here's the final graph. I copied it in from Desmos. You can see the local maximum is at negative 6, 766. Here's the inflection point at negative x equals negative 0.5, and there's the local min that I graphed. I found the height of the inflection point by plugging back into the original function f. And to see my Desmos work, let's see if I can bring that up. Yeah, here's the original graph on Desmos. You can see that, let's drag this over here. There was my original function, which I plugged in the values to see. And then here's the graph. I changed the scale so we could see all the points. We could see the max, min, and inflection point. So now I'm going to give a similar function. You'll go through all these exact same steps with a different function, but it'll be very similar in the setup. So please write up your solutions accordingly.